Okay, this is actually the first and second of our online lectures because I'm combining the lecture on far field diffraction and the review for exam 3. Now, first, I'm only going to talk about Fraunhofer or far field diffraction. And so let's be clear what that is. Let's say I have a double slit. So here's a double slit. If I have a screen that is relatively close, and I take the distance from one slit to a place on the screen and the other slit to a place on the screen, those lines are nowhere close to parallel, right? And so we're going to have to use some trig work to relate the two distances L1 from the slit to the screen, from slit 1 to the screen, and L2 from slit 2 to the screen. And it gets kind of difficult. So this is near field diffraction. And the solution for that was done by Fresnel, so it's called Fresnel diffraction. Far field diffraction is when you have your slits and the screen is very far away. So I draw the screen, I have to put the screen on the picture. But if the screen has the distance between the slits and the screen, which I'll call Y, and the separation between the slits, which we call lowercase d, and if Y is much, much greater than D, then if I draw those same lines, now in my picture, it doesn't look like it because I can't draw a picture where the Y is much, much greater than D. But in this limit, then, then L1, put that in the wrong order, L2 equals L1 plus D sine theta. And we get that equation because if they're very, very far apart, then if I draw a perpendicular there, I have an isosceles triangle, and the additional length is right here. And if I draw the line that goes out to the screen perpendicular to the screen, I have an angle theta here that is the same as the little angle right there, theta. And so geometrically, the opposite side is the difference in length, and that's going to be d sine theta. So this is the far field solution, which was solved by Fraunhofer. It's funny, H. So we're only going to do the Fraunhofer diffraction, the far field diffraction. So let's get going. So we have our setup. Now this picture shows multiple slits, but we're only considering 2 slits. So let us just pretend that everything down here doesn't exist. Well, let's back up and say everything down here doesn't exist. We have light coming in that is coherent. Coherent means it's all in phase. So we have these wavefronts, those little light blue lines. They're all parallel wavefronts. They're all in phase. They have their peak of the phase on the line, all going the same direction. So in that case, I could write that the electric field at each of the slits, so that's at the slits, is equal to some magnitude E0 times sine of omega t plus phi, where phi is some phase. That's telling you, okay, so at the slit, at time equals 0, it has this phase. Well, that phi is actually It's just depending on what you use for your time reference. So we'll set that time reference such that phi is 0. So we will just simplify this to E0 sine of omega t. But now, using the same thing I did before, I have here slit 1. Okay, I'm going to put the 1 out here. There's slit 1, and here's slit 2. And so the path going from slit 2 to point P is like that. And so that has length L2, whereas the path going from slit 1 to point P, that was supposed to be the, there we go, goes like that, and it has length L1. And as described for far field, the difference in those two, L2 minus L1, is equal to D sine of theta, where theta is the angle going from, I'll just take the midpoint here, to that point P. So this is angle theta. Well, how does this work mathematically? So here we've already laid it out, that E equals E0 sine omega t at each slit. But now when we get to the screen, it took more time to go from the slit to the screen. So the time it took to get from the slit to the screen is just using our standard equation that says that distance is equal to speed multiplied by time, then time is equal to distance over speed. And so in this case, the distance is the L, L1 or L2, and the speed is the speed of light over c. Now, just put delta t's there because that's what I have there. So that's the difference in time. So that means at the screen, I'm going to have E equals E0 sine of omega t prime, where t prime is equal to t plus delta t. So t is the time when the light hit the slit. T prime is the time when the light hit the screen. And so delta t is the additional time. So if I plug this delta t into there, then I have E is equal to E0 sine of omega times time plus L over C, because delta t is L over C. And then I just distribute the omega, so I have omega t is plus L omega over C. But now we just have to remember some fundamental physics. We know that frequency times wavelength is equal to the speed, in this case, the speed of light. And of course, frequency, or omega, is equal to 2 pi f. So if I solve that for frequency, frequency is equal to omega divided by 2 pi. So I can put in here, then that's equal to omega over 2 pi times wavelength. Well, I have omega over c here, so let's just rearrange this equation to have omega over c. So I'll divide everything by c and multiply everything by 2 pi over lambda. So that gives me omega over c is equal to 2 pi over wavelength. So I plug that in for the omega over c right there, and I have the electric field at point P on the screen is going to be E0 sine of omega t plus 2 pi L over lambda, where L is L1 or L2, depending on which slit I went through. Now, of course, at the screen, I have light from slit 1 and slit 2 meets together, and so the electric field at point P, is equal to electric field from 1 plus electric field from 2. So that's going to be equal to E0 sine of omega t plus, and then I had, I should remember this, right? 2 pi L1 over lambda plus E0 sine of omega t plus 2 pi L2 over lambda. So that's the electric field at point P that came through those two slits. So now we do that, we combine them. So here is what I just wrote. And then we use a little trig substitution, that is sine of A plus sine of B equals 1, or is equal to 2. 2 sine of A plus B over 2 cosine of A minus B over 2. Now, it doesn't matter if it's A minus B or B minus A, because cosine of A minus B over 2 is equal to cosine of B minus A over 2. That's cosine of minus theta equals cosine of theta. So it doesn't matter which way you do it. And so using that trig definition and the fact that we have E0 that we can factor on both sides, then we can write the equation for the electric field at point P on the screen is equal to E0 times this stuff. Well, we have a rule that says the intensity is proportional to electric field squared. So if I square that, I'm going to have E0 squared times 4 sine squared of omega t plus pi times L2 minus or plus L1 over lambda multiplied by cosine squared of pi L2 minus L1 over lambda. So there's an equation for the intensity as a function of time. Now, nobody's sitting there and calculating, oh, it got brighter, dimmer in the time it takes for one cycle. I mean, one cycle for light is like 10 to the minus 14 seconds. So clearly we're not sitting there and watching that flicker. Instead, we say the intensity averaged, and this is averaged over time, the average of sine squared goes from 0 to 1. It goes like this. And so the average is 1/2. So that's going to be times 4 times 1/2 for the average of the sine. I'm going to actually do some color coding here. Let's see what happens if I change that color to red. Hey, it changed all but one stroke. And so the average of that stuff in red is 1/2. And then if we do the time average of the cosine term, well, that cosine term, the sine average of this is just the same as what we have. It's no different. And so that's going to be times cosine squared of pi times L2 minus L1 over lambda. So we will combine and call this here our peak intensity that we get from the double slit. And then we have this modulation, this spatial modulation, because L2 minus L1 has to do with distance. In fact, we already worked out previously that L2 minus L1 was equal to d sine theta. And so what we have is I, the average intensity, is equal to the peak intensity times cosine squared of pi d sine theta over lambda. So there's the equation for the far field solution for the intensity as a function of the angle away from going straight. Now this is a little more involved than what we did in class, but it gives us both the situations for maximum and minimum. So let's just do that real quick. Maxima. What's that? Erase sesame. Well, it's not going to erase. Maxima. The maximum of cosine occurs at angles well, cosine squared is a maximum of 1 when pi d sine theta over lambda is an integer multiple of pi. M equals 0, comma, plus or minus 1, etc. I never give myself enough space. It's right down below. So m is any positive or negative integer, including 0. Now, of course, we should recognize there is a pi on both sides, so cancel that. And that gives us d sine theta is equal to m lambda. So that's our equation for maxima. Now for minima, it's pretty similar. Cosine squared pi d sine theta over lambda will equal 0 for a minimum, which occurs when the argument of cosine is pi over 2, 3 pi over 2, etc. So when pi d sine theta over m, or over lambda, equals m plus 1/2 pi, where again, m is any positive or negative or 0, any integer. And so just like before, if I solve that by multiplying across by lambda and canceling the pi's, I have d sine theta is equal to m plus 1/2 wavelength, where m equals so there's my equation for minima. So I got the same maxima and minima equations that we got in the general physics class, but what we have that we didn't have in general physics class is an equation that will tell us what the intensity is for any angle, not just where we have maxima and where we have minima. So that's our solution for the far field for a double slit. And that's ultimately not very difficult. By the way, if you look at this picture, you'll see that they have tried to illustrate that L is what they called it, I called it Y, is much, much greater than D. And because it's much, much greater, these lines are effectively parallel. So this compressed scale, this would take, like, let's say 100 pages, is spread out there. So that's why it looks funny. All right, so that's double slit. Now let's turn our attention to the single slit. Now the single slit is more difficult because you have a continuum of rays coming through. What we did just before was 2 different rays coming through. Now we're going to have a continuum of rays. Now if we take the maximum difference in length, remember doing the far field, if this distance here is capital D, then the maximum delta L, so I'll put delta L max, is equal to D, capital D, sine theta. But if I'm right here, the first ray has a distance, I'll call it L0. And then the second ray that's up just a little bit is going to have just a fraction of the total max. So I'm going to say that I break it into n slits. And so the nth slit will have a length sub n is equal to the length of the 0th slit plus the nth over capital N. That is, if I had two slits, that the first, or if I, it'd be 1 over 2 if I had, more, say 1 over 200 times the maximum of d sine theta. And so if I put that into an equation, the electric field for the nth slit is the total electric field that comes through this entire slit divided by capital N, the total number of slits, so n slits, and then sine of omega t plus 2 pi L for that slit over lambda. But then substituting what L for that slit is, we have the L0 term right here, and then we have the lowercase n over capital N d sine theta here. So if you look carefully then, this would be, there's a missing line, if you will. The missing line is E0 over N sine of omega t plus 2 pi L0 over lambda plus 2 pi over lambda times lowercase n over capital N d sine theta. And so we take the 2 pi over lambda and the d sine theta, and we bring those together and we just call that beta. We're calling that beta just to make our writing simpler. So we define beta as 2 pi over lambda d sine theta. And so this is the electric field that came through the nth slit at point P on our screen. So just like before, now we need to add up all of these electric fields. And what we're going to do is we're going to add these up as vectors, as phasors, as we call them, phase vectors. So we have this here. We're just going to arbitrarily set that to 0. That's our reference phase. And so the first, for n equals 0, you have an angle. So here's our phase angle. And for lowercase n is 0, you have an angle of 0. So the first one is drawn horizontally. But then the second one we have, 1 over capital N times 2 pi over lambda d sine theta. So it's at some slightly increased angle. Remember, when we add vectors, we just add them tip to tail. And so we add each one of these tip to tail. And then after you've added them all tip to tail, the resultant is the vector that goes from the starting point to the ending point. So this green arrow represents the total electric field at point P due to adding up all of these different electric fields. Well, I broke this up into discrete slits, right? But we don't have actually any slits. It's continuous. So what we're going to do is, what I've been describing is that E total is equal to the sum from n equals 0 to capital N of E sub n. But if it's continuous, this will become an integral. I just put dE sub n there to make it simple. So how do we do that integral? Well, we're going to do it graphically. Surprisingly, we are not doing any actual calculus right here. Even though it's an integral means add them up, and we can add these graphically. If I have an infinite number of slits, then each one has an infinitesimal change in angle, and that's the definition of doing the integral. We add them up tip to tail, and so if you get rid of all of my little arrows, you're just going to have a circular arc that you're drawing. And so we're going to use geometry to do the integral. So here I have a picture that better explains that, well, not there. Here is a picture that better explains the integral. So we have this E0, that is the total electric field that went through the slit. So E0 is the electric field that went through the slit. And E theta 0 is the electric field, I'll point on the screen. Now, just some things to explain what this diagram is so you know where it came from. So we have adding these up along that arc. We know that the first one that we drew had a phase angle of 0. So there's the angle for the first one. The last one has a phase angle of beta. And so we just bring that down here. We just extrapolate from the last one down. And we know that this angle here is beta. And using simple trigonometry, this angle here has to be 180 degrees minus beta. Well, continuing on with trigonometry, by definition, because we're doing a circular arc, then the radius makes a perpendicular angle with the arc. And so we have sketched a four-sided shape here. I'll do the four sides in green. So there's one side, another side, another side, another side. And we know the sum of the interior angles of a quadrilateral is 360 degrees. So sum of the interior angles equals 360 degrees equals, and I'm going to call this whole angle here alpha. So alpha plus 90 degrees, that's 90 degrees right there, plus 180 degrees minus beta, plus 90 degrees. Well, of course, if you just add those up, 90 plus 180 plus 90 is 360 degrees, plus alpha minus beta. So we get from that alpha must be equal to beta. And so that's how we get this angle here. Notice it's beta over 2 and beta over 2 because it's split in half. And now you're wondering, why, pray tell, is it split in half? Well, we have a couple trig relations that we can do. First, arc length is always S is equal to radius times the angle. So in this case, the arc length is E0. So that gives us E0 equals radius times my angle, which was alpha, which turned out to be beta. So there's an equation that relates the total electric field that went through the slit to this radius. And you might be asking, what is the radius? Important. It's the radius in the diagram, okay? Times beta, where beta is the maximum angular shift between the first and the last rays going through the slit. So that's the first thing we do. Now the second thing is going to be trying to find E theta 0. Now let me draw a red triangle that, of course, this is why we have the angle split in half. With this red triangle, once again, we have a right angle here, and this side is E theta 0 over 2, and the hypotenuse is R. So using trig, we have sine of theta, and theta here is beta over 2, so let's be a little more careful. Sine of beta over 2 is equal to the opposite side, E theta 0 over 2, divided by the hypotenuse, R. Or solving that for E theta 0 is equal to 2R sine of beta over 2. Now I'm going to take these two relations and just divide them by each other. It's the easiest way. So I'm going to put E theta 0 over E0 is equal to 2r sine beta over 2 divided by r beta. What was the point of this? Remember I said r doesn't matter? R cancels here. We usually write this as sine of beta over 2 divided by beta over 2. So E theta 0 equals E0 times sine of beta over 2 divided by beta over 2. And since, by definition, intensity is proportional to the electric field mod squared, then I have intensity for theta but this here is just going to be the incident intensity. So we have I for theta is equal to I0 times sine beta over 2 over beta over 2 quantity squared. So that's the intensity as a function of angle. Now remember what beta is. Pi d over lambda sine theta. Oh, there's a, oh, yeah. It was 2 pi d over lambda sine theta. So that's where the 2 disappeared to. So there's the equation for the intensity as a function of angle for the single slit. And so this is just showing the work that I've done and getting to the entire solution with one glowing error. I thought I had that there, but it doesn't have the square. That square is kind of important. So there we have the intensity function. Now there's a couple important things. Important thing number one. What is intensity at theta equals 0? If we look at this equation, we'd say, well, the intensity is at theta equals 0. I have intensity is equal to I0 times sine of 0 over sine of 0 quantity squared. And we see that's a problem. That's a problem because it's 0 over 0. 0 over 0 could be 100, it could be 0, it could be infinite. So how we determine what actually happens there is using L'Hopital's rule. So the intensity as theta approaches 0 is equal to I should put limit as theta approaches 0 for the intensity. And now I have to do L'Hopital's rule, which you do the derivative of the top by the derivative of the bottom. Well, I want to make my life a little easier. I'm going to do the square root of intensity, because if I find the square root of the intensity, I can just square it and I'll know the limit of the intensity. So if I do that, I'm going to have derivative of the top divided by derivative of the bottom so I have to do those derivatives. And so on the top, the derivative of sine cosine pi d over lambda sine theta. And then derivative of the inside is pi d over lambda cosine theta. For the bottom, pi d over lambda cosine theta. So if I take the limit as theta approaches 0, I'm going to have, well, first things first, cosine of 0 is 1. And so this whole pi d over lambda times 1 will cancel out. And sine of 0 is 0, cosine of 0 is 1, so that's equal to square root of I0 times 1, which means that we're going to be at I0 at our peak intensity at theta equals 0. So theta equals 0 is a maximum. Now, if I want to find minima, that's actually easy. I find the minima by just saying, okay, minima are going to occur when the numerator is 0, unless the denominator is also 0. Well, the denominator was 0 at 0. That's why I did this first one. The denominator is not going to be 0 again within pi over 2 to minus pi over 2. That's our range, right? Your diffraction can't extend beyond pi over 2. So sine theta is just going to go to 1 at the extremes. We're just dividing by bigger numbers. We go out, so the magnitude is dropping as we go away from the center, which makes sense if you look at the picture. By the way, here is the center, and you see that was a peak. So for the minima, we need sine of pi d over lambda sine theta equals 0, which has then the requirement that pi d over lambda sine theta is equal to an integer multiple of pi, where m can't be 0 because we just ruled it out for a minimum. So it's plus or minus 1, plus or minus 2, etc. So just like before, we will cancel the pi's, and we have d sine theta equals m lambda, where m is equal to plus or minus 1, plus or minus 2, etc. And that's the equation for minima. Now maxima is a much harder process. I'm going to do that actually at the end of the lecture, so I'm not going to find the maxima right now. Last thing for the technical lecture here today is, what if you have a double slit with a finite width, instead of just a point? Because what we assumed before was that our single slit it was just a point. But of course, the amount of light you get through just a point is virtually nil. So what you really have is the product of the double slit and the single slit results for the intensity function from a two-slit grating. All right, so that is our showing how the waves actually work with diffraction grating for Fraunhofer diffraction. Now let's review for exam 3 real quick. We have 3 things that you can see on this test that will be specific to calculus. One would be, and I put this as one statement, but it's really 2, combining Maxwell's equations to derive a wave equation, and then showing that a function is or isn't a solution to the wave equation. Number 2, showing that Fermat's principle predicts Snell's law. Number 3, finding conditions for constructive or destructive interference with a single slit or double slit. So let's just look real quickly at those. Here's Maxwell's equations. Maxwell's equations, Gauss's law for electric, which gives us that a charge produces an electric field. Gauss's law for magnetic, a magnetic charge would give us a magnetic field. Faraday's law of induction that says a change in magnetic field gives us an electric field. Ampere's law, which says that a change in electric field gives us a magnetic field. Also, a current gives us a magnetic field. Now, to derive an electromagnetic equation, we use the differential forms of Maxwell's equation. And first we went through this, so just go back and look at the slide if you want to go through it in detail. But we had take the curl, that's del cross x, of both sides of the differential form of Faraday's law. So Faraday's law, differential form. So you start with del cross E equals del cross, and actually I should have used some color coordination here. Remember del cross, that's the curl of. So there's the first step. Then you use this vector identity. Of course, I don't expect you to memorize this vector identity. I don't expect you actually to memorize this sequence. I want you to know how to do it, but you don't have to have it memorized, right? If I give you the steps, you should be able to go through and do it. So the vector identity for the del cross E, that's the left side, is equal to del dot E. Minus del dot del, which we usually write as just del squared without a vector, E. And then on the right-hand side, we have del cross, and then minus d dt of B. Okay, that seems good enough, but what we're going to now do is rearrange. So first of all, del dot E, if we plug in del dot E is rho over epsilon 0. Wait a minute. Del times, not del dot. That's like, it's not a vector. That wasn't supposed to happen. Minus del squared of E equals, and I'm going to bring the minus ddt out because the del is a spatial derivative, and so I'm just having minus d dt of del cross B. But del cross B, going up here, del cross B is this here. And now we're actually only one step away. And what is that step? If we're doing this in a vacuum, the charge density is 0 and the current density is 0. And so what we have after doing all of this work is minus del squared E equals minus d second dt, oh, I forgot, minus mu epsilon 0, d second E dt squared. And of course, those minus signs, we can just cancel those out and make them both positives. That, my friend, is a wave equation. The wave equation should be del squared f, whatever f is, equals 1 over c squared d second f dt squared. And of course, I have a vector in the del squared. There's no vector on the del squared. That is a scalar. And so this is a wave equation with speed of light is equal to 1 over the square root of mu naught epsilon 0. So that's the derivation. You're not, if you're going to do the derivation, I'm going to give you the steps and you just have to follow the steps. Otherwise, I could say, suppose E vector is equal to E0 vector, which is a constant, times sine squared of omega t plus kx. And I ask you, is this a solution to that wave equation? Well, to test it, you simply do them. So you have del squared E, since this is only x, is just going to be equal to d second dx squared E, which is going to be, if you take the derivative, you have to do dE dx is equal to E0 times 2 sine omega t plus kx times cosine omega t plus kx times derivative of the inside, k. And so d second E dx squared would be derivative of sine is cosine omega t plus kx times k times cosine omega t kx again, k. And then plus sine of omega t plus kx times derivative of cosine, which is minus sine omega t plus kx, k squared, or equals E0 vector times 2 k squared cosine squared omega t plus kx minus sine squared omega t plus kx. And so that's what I have for del squared E. Now I also have to do d second E dt squared. dE dt is equal to E0 times 2, and it'll still be 2 sine of omega t plus kx cosine of omega t plus kx times omega. d second E dt squared is equal to E0 2 cosine of omega t plus kx quantity squared times omega squared. And just because the work is so similar, minus sine squared of omega t plus kx omega squared. And so if I compare these, then I have the E0 vector 2 k squared cosine squared of omega t plus kx minus sine squared of omega t plus kx. Is that equal to, so I'm testing, is that equal to E0 squared to omega squared times, and this here was the same thing, and then we had times mu 0, epsilon 0, or over c squared. So I'm going to put the over c squared. And so does that fit? This here and this here were the same. And in fact, the E0s were on both sides. The 2's were on both sides. So basically what I have is c squared is equal to omega squared over k squared. Certainly that is acceptable. That's workable, and we actually have the speed is equal to plus or minus. Don't have to put a plus square root because they were squared, omega over k. And so that is a fit. It's a solution to the wave equation. So the testing is take the second derivative of the left-hand side, the second derivative of the right-hand side. If you have a function in the end that doesn't involve t and x, then it's a solution. If it involves t and x, it's not a solution. So that's one thing that could be on the test. Next thing, Fermat's principle. Remember Pierre Fermat, or Pierre de Fermat, suggested that light takes the shortest time to get from point A to point B. And if you use Huygens principle, you can actually do the calculation. So we did this calculation. I'm not going to repeat it. You can go back and look at the lecture on that. But you should be able to do this calculation. You should be able to say, okay, I want to find what x is if it's a separation of d horizontally and A in medium 1 and B in medium 2. I want to find the x that minimizes the time it takes to go from point A to point B. So you're going to be using, since V or D distance, better use something besides distance, S for distance is equal to VT. Then if you solve for T, T is equal to S over V. So you find the time in medium 1, the time in medium 2 as a function of x. And then you take the total time, you take the derivative, then you have the equation for total time, you take the derivative of the total time equation with respect to x, set that equal to 0 at x0, and then you just solve to find an equation that in the end will have sine theta and sine theta 1 and sine theta 2. So you should be able to replicate that. The final thing, find the equations for maxima and minima from a single slit. Now we already looked at the minima equation. Here I say the maxima and the minima. And I have a hint here. You wouldn't have the hint on the test, but I will put it here because I want you to know how to be ready in case this comes up on the test. So the first thing is I'm going to let u equal this. Why? Because it makes my life easier. This is then just I0 times sine squared of u over u squared. And so if I take the derivative of that, to find minima or maxima, I take di d theta, evaluate theta 0 is equal to 0. That is the way we find maxima or minima. And so that's going to have the I0, and then derivative of the sine squared u over u squared is going to be derivative of sine squared 2 sine u times cosine u over u squared. And I know I have to have the chain rule, so out here du d theta plus sine squared u, and then that was over u squared, so that's going to be times a minus 2 over u cubed. Yeah, that should be right. And so in doing that, then I'm going to have equals I0. And notice there's a 2 in all the terms, so I'm going to put the 2 out here. There's a u cubed here and a u squared. I'm going to actually factor out the u cubed. And so I'll have, oh, and there's a sine u in all of the terms. So I'm going to factor out a sine u. And then I'm going to have u cosine u minus sine u, and then du d theta. So here I've done everything in terms of the u's. Now I'm going to substitute in kind of specially. So this is 0 equals I0, 2. That's constants. Not worried about constants. 1 over parenthesis pi d over lambda sine theta q. There's my first part. My second part is going to be sine of pi d over lambda sine theta. My third part will be, and here I'm just going to put u cosine u minus sine u. I'm leaving that in terms of u. And then my final term will be the derivative of u, which is pi d over lambda cosine theta. So notice I actually have 4 terms in parentheses. Those 4 terms are terms that depend on theta. And so I have 4 possible solutions here. Solution 1, 1 over pi d over lambda sine theta quantity cubed equals 0. That would require sine theta being infinite, which can't happen. So there's no solution there. But it rules out, it fails at theta equals 0 degrees, or theta is equal to 0 radians, because we have 1 over 0, we have no solution there. Okay, going to the next one. Solution 2, sine of pi d over lambda sine theta equals 0. That's going to be true anytime this argument is an integer multiple of pi. So we're going to have pi d over lambda sine theta equals m pi, where m is equal to 0, comma, plus or minus 1, comma, plus or minus 2, comma, dot, dot, dot. But keep in mind, we just ruled out that we cannot have theta equals 0, so we cannot have m equals 0. Cancel out the pi's, and what we get is d sine theta is equal to m lambda. M equals plus or minus 1, plus or minus 2, etc. And we already showed those are the minima. So good. That's good to have a solution, right? That agrees with what we found before. Now the next one is the hard one, especially if you can't spell solution. U cosine u minus sine u equals 0. Or u is equal to tangent u. This is a transcendental equation. You can plot this. I'll put u on this axis, and then I will make a graph of so that is y equals u. And then I add on to this my graphs for a tangent of sorry about the sound effects, but it's the way my brain works. And you have all the tangent curves that go on there. Now, if we look, we have a crossing there, a crossing there, a crossing there, a crossing there. Those are all solutions. Now, how do I actually find these? I mean, I can go ahead and I can do this I usually do it with a spreadsheet. But for today's purposes, I went to Wolfram Alpha. Obviously, you would not go any further than this. You wouldn't have to do the solution on the test. But this gives us solutions that u equals 0, comma, plus or minus 4.4934, comma, plus or minus 7.725, comma, plus or minus 10.90, and it goes on and on. So you have a bunch of different solutions there. And remember, u was equal to pi d sine theta over lambda. And so now you can solve for what you have for d's, or excuse me, not for d's, but for thetas, that will give you, in this case, constructive interference. So these are maxima. And this 0 really does belong in the maxima. We saw that from our usage of L'Hopital's rule. Now there is a final solution here. Solution 4 when pi d over lambda cosine theta equals 0. Well, the solution for that is real simple. Theta is equal to plus or minus pi over 2. Well, yeah, that's a minimum. You don't have any light that goes past plus or minus pi over 2. So that's kind of a throwaway, but that's also a minimum condition. So there you have finding the maxima and the minima for a single slit diffraction. So those are the things that you need to be able to do for the exam. If you have any questions, of course, feel free to contact me, and I hope that you feel a little confident